Hello everyone, welcome to COMP251 Data Structure and Algorithms. In this video, I'm going to talk about some applications of stacks and showing you very interesting algorithms that we can write using a stack. Last week we have talked about a stack. A stack is a restricted form of a list. It is a collection of items that keeps the items in linear order, but allows to access to the items from just one side of the list, that we call it the top of the stack. You can only add an item on top of the stack or remove an item from the top of the stack. So because of that, a stack is also called first in, last out data structure. There are many applications for a stack, many parsing algorithms, converting Infix to postfix expressions, calculating postfix expressions. Computers use a stack to implement method calls. These are actually the things that I am going to talk about them today, because they are very interesting problems in computer science. So first I need to just define this notation, that what we call infix notation, postfix and prefix. The algebraic expression that you have already learned about in a school, or you daily use them, we write them in the notation of the infix. So it actually basically means that you put the operator between the operands. So when you wanted to write a plus b, you would write it as a plus b. A and b are the operands, right? And plus is the operator. So the operator comes between the operands. And this is actually the notation that we are used to as humans. But this notation is actually very difficult to work on when you are thinking of it as a programmer, as someone who is going to write a compiler that wants to actually tell the computer what to do with this expression and calculate it. There are different things that makes the infix notation difficult. The first thing is that infix notation is ambiguous. Sometimes you need to actually use parentheses to make sure that how to actually interpret the expression. So if you see something like this, an expression like this, a plus b multiplied by c, you can see that there are two different ways to interpret this expression. I can actually understand this expression and interpret it as first actually add a plus b and then multiply the result to c. Okay, this is one interpretation. The other one is that first multiply b to c and then add the result to a. So which one is going to be the correct interpretation? Of course, for us as humans, we just know that we give the higher precedence to multiplication. So if you see an expression like this, you would understand it as this interpretation. You would first multiply b to c and add the result to a. But this is just a rule that we know it. But the computer doesn't know that. This is something that when you are implementing a calculator to calculate some infix expression, you should actually consider that when you are writing your program, right? And we call these type of rules precedence rules, that say that, for example, multiplication and division has higher precedence than addition and subtraction. Okay, so these are some rules that we should consider when we are dealing with an infix expression. The other thing is that what if you get an expression like this? How you are going to interpret this? You see that I have two operators here, division and multiplication. Both of them have the same precedence rule, in fact, for us, precedence level. So how I'm going to interpret that? I'm going to first multiply B to C and then divide A to by the result, or I'm going to first divide A by B and then multiply the result by C. Which one is the correct one? Again, we as humans knows that if we are seeing some operators which have the same precedence level, we read the expression from left to right. So we give the higher precedence, we give the, I shouldn't say precedence, we don't call it precedence, but we actually apply the operators which are of the same precedence from left to right. So these kind of rules that we know as humans is going to be called associativity rule, that all the operators are left associated. So you read it from left to right and you apply them from left to right. So again, this one is the correct interpretation. You would first actually calculate A divided by B, and the result will be multiplied by C. So what if I meant actually this expression or this expression? In those cases, you have to use parentheses. You have to put A and B inside parentheses, and using the parentheses, you give higher precedence to calculating A plus B first, and then the result will be multiplied by C. So this actually just shows you that yes, not only we have to deal with this type of the precedence rules and associativity rule, but also we need to deal with parentheses. So we need to add parentheses, which makes working with the expression actually more difficult. When I'm actually talking about difficulty here, you should think of it as, as a programmer, as the one who is writing a kind of compiler, parser, that reads the Infix expression, and you wanted to actually interpret that and evaluate it. Write a program to evaluate some Infix expression. Okay, so this is our goal. So now it's time to actually introduce two other type of notations that they are in fact simpler in terms of this ambiguity, removing ambiguity, having parentheses. In fact, these notations doesn't need any of these. We don't need precedence rules in these notations, because their notation basically apply all of the rules, the precedence rule, the associativity rule, and we don't need to use the parentheses when we are writing them. So kind of for the computer, when we are actually thinking about in the context of computer science, they are going to be simpler notations, although because we are not used to it as human, they are going to be more difficult for us to read. But in terms of writing some programs, they are going to be simpler. So let's actually introduce those notations. The first one is prefix, which actually just means that unlike infix notation that put the operator between the operands, prefix notation puts the operator before the operands. So infix notation would write A plus B in this way, put the operator between operands. Prefix notation put the operator before the operands. Okay, so A plus B will be actually written as plus AB in the prefix notation. Sometimes it is just called Polish notation as well, just because the mathematician who invented these notations was Polish. And the other notation was reverse Polish or postfix notation that just very similar to the prefix notation. It just puts the operator after the operands, so A plus B will be written as AB plus. Okay, sounds simple, but when you are actually writing some more complicated expressions, it would became more complicated, for us as humans, of course. So here you can see some examples of expressions, infix expressions and their equivalent prefix and postfix expression. You can see that for those cases that we have the parentheses, we don't really need parentheses in their postfix or prefix format. And the reason is that, for example, when you are writing a plus b multiplied by c and a plus b inside the parentheses, you meant to apply the this addition first, and then you wanted to multiply the result to c, right? So when you are looking at the prefix notation, you can see that when you are reading this expression, so for plus, the operands should come after, right? So it's going to be A and B. And when you are reading it, you can see that there is no other way to interpret this expression. This is not going to be ambiguous anymore. You cannot apply you cannot apply multiplication to B first, because if you are going to multiply the multiplication, you need to have the operands after that, right? But after multiplication, in this notation, there is plus, right? In this expression, in this prefix expression. So it's not possible to apply multiplication. You have to apply the addition first. We don't need parentheses in these notations. So let me actually show you some examples. Specifically, I'm interested in postfix notation. The reason is that at the end we will see, when we are working as a programmer, as the one who is writing a program to calculate an expression, postfix notations are going to be much easier to work on than prefix notation. So we are going to stick to postfix notation. The whole idea here is that in the postfix notation, you can see that the operator comes after the operand. So whenever you see the operator, you can just look back and find the operand. So kind of it's much easier to detect the error or see if there is anything. I mean, it's going to be much faster. Unlike in the prefix notation, that the operator comes and you have to wait until you see the operands. So it actually makes it, a little bit more difficult to detect the errors and make it actually just, slower in detecting the errors. So postfix notation is going to be preferred here. So let me actually just show you some example of the postfix notation and how we calculate an expression which has been written in postfix notation. Look at this expression. This is the infix expression, 3 plus 4 multiplied by 5 minus 6. If I'm going to write the equivalent postfix notation for this one, this is going to be like something like 3, 4 plus, you can see that I wanted to actually just convert this part, right? I wanted to calculate 3 plus 4 first, so this part needs to be written first. I just read it from left to right, okay? And then you have an operator which is multiplication. The result of this one needs to be multiplied by 5. So what I need to do is I need to consider the operand first, and then the multiplication, and then the result of here needs to be subtracted by 6. Okay, so then you have to, this is one of the operands and the other one is here. So far you have this operand and the rest is going to be the next operand and then the operator. So the result is going to be 3, 4 plus 5 multiply, 6 subtract. So how I am calculating this, if you get a postfix expression, how you are going to actually evaluate it. This is the first problem that we are going to solve. I am looking for an algorithm to you give it a string which shows a postfix expression, and we wanted to evaluate it. So let's see that as humans, how we evaluate a postfix expression. So as humans, what you need to do is that you started from left to right, just like any other algebraic expression. You read from left to right and try to evaluate the expression. So the first thing that you read is 3. So I can't do anything with this operand. This is just a number, right? You wait. The next value, the next token is going to be 4. This is again an operand. I can't do anything, so I'll wait. The next operand that I will see is going to be, the next token that I will see is going to be a plus. Okay, so I see an operator, and I know that this is a postfix notation, right? So if I am seeing an operator, I should have seen the operands for that before, and their operands should come just before this operator, right? So I should just look back 2 steps before, and yes, the operands here are going to be 4 and 3. You add 4 and 3 to each other, and the result is going to be 7. So it's just like, instead of 4 and 3, and actually the result of this one, whatever is going to be the result, I can just ignore 3 and 4 and just write the result of this addition, which the result is going to be 7. So I write the result and keep going on reading the rest of the postfix expression. So the next token is going to be 5, right? Again, this is an operand, so I will wait because I can't do anything with just this number. The next token is going to be a multiplication. Again, I am seeing an operator. So if I'm seeing an operator, there should have been the operand for this one. So I just look back 2 steps before to see what are the operands of this operator. One of them is going to be 5, and the other one is going to be 7. In fact, the other one was the result of this expression. I have already calculated and put the result there. So I just need to read 5 and 7 and say that, okay, 5 plus 7, the result is going to be, 5 multiplied by 7, the result is going to be 35. So again, I can just write, instead of the whole part here, I can just write 35. This is the result of the expression so far until this point that I have read. This is 35. So I will continue reading the rest of the expression. The next token is going to be 6. Again, this is an operand. I can't do anything with that. Wait. The next token is going to be a subtraction. So you need to, this is an operator. So you have to just read the previous 2 operands for this one. The previous 2 is going to be 6 and 35, right? Subtract 35 from 6. So be careful here, the order is important. This one is the left operand and this one is the right operand. So 35 minus 6, the result is going to be 29. Okay, so this is the way that we humans will deal actually with a postfix notation, how we can write a program for that. Let me actually show you another example here. This is another example. Again, this is a postfix expression. How can I actually work with that? So you started reading it from left to right. Okay, be careful about what I'm explaining here. You are reading it from left to right, token by token. This is important because we are going to write an algorithm for this. So the first token is going to be 3. This is an operand. I can't do anything with that, so I should keep it. So 3. The next token is going to be 4. This is again an operand. I can't do anything with that, so I should keep it. The next token is going to be 5. Again, this is an operand. I can't do anything with that, so I should keep it. So you can see that it doesn't really matter that if I keep actually reading a couple of operands, more than one, and you just need to keep them because you need them later. It's not like an infix notation that you see an operand and then an operator and then another operand and just apply it, right? So I will continue. The next token is going to be an operator. Okay, I'm seeing an operator, so I should have seen the operand for this operator just before that. Be careful, just before that. So this multiplication needs to be applied on the previous 2 items that I have seen and the closest items that I have seen, right? I don't care about 3. The closest item that I have seen, this is going to be 5 and 3. Sorry, 5 and 4. So you apply the operator to these two operands and calculate the result and keep the result. So instead of 4 and 5, I will need to keep 20. And from before, I already actually just keep 3 as well. You shouldn't lose 3, right? Because you need it later. So far I have 3 and I have 20. Then you continue read the next token. The next token again is going to be an operator. It doesn't matter if you have actually a couple of operators coming in a sequential matter. The only thing that matters is that you should just look back and find the operand for them. So for plus, I should just look back and find the two operands for them. One of them is going to be 20, the other one is going to be 3. Sorry, so as 3 plus 20, the result is going to be 23. And now I'm going to keep 23 and nothing else. The next token that I'm reading is going to be 6. So you keep it. So far you have 23 and 6. The next token is going to be minus. Okay, this is going to be an operator again. You should look back and find the closest to operand that you have seen. So they are here, 6 and 23. So I'm going to apply this minus between them. This one is going to be the right operand, this one is the left operand. The result is going to be 17. Okay, so I'm done. This is going to be the result. One thing that you should have already noticed is that when I am seeing these tokens one by one, I'm actually telling you that if you see an operand, you have to keep it. Where we are going to keep those operands? This is a question. Are you going to put it in an array, in a list? Where? You should keep them somewhere, right? In some variables where you are going to keep them. So the thing is, we need a data structure to keep these operands that they are waiting for their operator to be applied on them, right? So exactly here is the idea that so far here I kept these in in a storage. I kept them somewhere, and then after that I had actually that storage like this, and then here I had them in this way, and then here I have them in this way. So the thing is, that data structure that we are going to use here is going to be a stack. The reason is, when you are actually dealing with the operators, you are looking for the previous two closest operand. So it's just like exactly the behavior of a stack, right? The first thing that you put inside the stack is going to be the last thing that you have inserted to the stack, pushed to the stack, is going to be the first thing that is coming out. This is exactly the behavior that I want. When I'm looking at this multiplication, I'm looking for the closest operand, which are going to be 5 and 4. We need a stack to calculate this. And the whole idea here is that, okay, whenever you see this is going to be a very simple algorithm. Whenever you see an operand, you just need to start reading the tokens from left to right. And whenever you see an operand, just push it to the stack. Okay, so think about it in this way. Whenever you see an operand, you just push it to the stack. Another operand, push it to the stack. Another operand, push it to the stack. Whenever you see an operator, what you are doing is just look at the stack, get out the operands. So you need to apply 2 pops because these operators are going to be binary. So I need 2 operands for them. You need to get out 2 operands, right? Apply the operator, get the result, and then push it back to the stack because you need it for the further calculation. Okay, so this is all of the whole algorithm. Whenever you see an operand, push it to the stack. And whenever you see an operator, apply 2 pops, calculate the operators over the result, and push it back to the stack because you need to keep it for the further actually calculation. So let me actually just apply this algorithm over this example. It makes it much easier to understand. I mean, I have written more examples for you as well, so you can actually go through the slides, but let me actually go through this example here. You can see that this example looks very complicated for us as humans, but I'm going to just apply the algorithm that I explained to you. You read the input expression left to right, token by token, and for each token I have two cases. Either this is going to be an operand or an operator. If it is an operand, so this is going to be the whole algorithm. Read the input expression from left to right, token by token from left to right. Left to right. Okay, for each token, let's just call it E. For each token E, there are two cases, right? If E is an operand, what would happen? You just push it to the stack, right? Push E to a stack. If E is an operator, you have to apply two pop from a stack, or let's just actually write it in this way. I can actually even write this one this way to just make it more readable. Stack dot push E, and here right operand will be stack dot pop. The first one that you pop is going to be it's going to be the left operand. A stack dot pop, and then the second pop that you do, for example here, this one is going to be the right and this one is going to be the left, right? If you, for example, push 1 and then you push 2 and then you push 3, when you are popping this one, the first pop that you would apply is going to be the left operand, and the second pop is going to be the right operand, right? That's why I'm writing it in this way. And the second pop, stack dot pop, and then you apply the operator over them. Okay, the result is going to be, let's just call it O. Apply E on, why did I write off? On R and L. Push or a stack dot push. Okay, so this is the whole algorithm. At the end, when you are done with reading the whole input, here you just need to pop the result from, the result will be the whole result is going to be in the stack. You just pop it out and this is going to be the result, right? A stack dot final pop. Okay, So what I'm going to do here is just apply this algorithm over this example that I have here. Okay, so I'm going to use a different color. You just read the token from left to right. The first token that I'm reading is 1. This is an operand, right? You push it to the stack. The next token is going to be 2. This is an operand. You push it to the stack. The next token is going to be 3. Again, this is an operand. You push it to the stack. The next token is an operator. So what this if condition tells me, if E is an operator, you pop and the result is going to be L. So L will be 3. You pop it. You call another pop and the result is going to be R. And it's been removed from the stack. Okay. So you apply the operator over R and L. So this is going to be the result O is going to be R plus L, which is going to be 5. And then you push 5 to the stack. So 5 is going to be in the stack. Okay, so I will continue reading the next token. This is going to be an operand. 4 is an operand. You push it to the stack. The next token again is an operand. And you can see that I don't really care about the, actually I don't care about the orders that, okay, I have a couple of operands, I have a couple of operators coming sequentially. I just need to just follow the algorithm that I have. If it is an operand, do this. If it is an operator, do this. So 4 will be pushed, then 5 will be pushed, then 6 will be pushed, right? Then the next token is going to be multiplication. This is an operator. What I need to do is 1 pop, L will be 6. Another pop, R will be 5. So just let's remove them. Then you apply E, the operator, over R and L. So O will be R multiplied by L. This is going to be 30. 30 will be pushed to the stack. The next token is going to be E. So again here, you have an operator. You apply 2 pops. The first pop is going to be L. The second one is going to be R. So they are removed from the stack, right? You apply the operator. Here you can see that it is important which one is L and which one is R. So the result of O is going to be R minus L, which is going to be minus 26, and this is going to be pushed to the stack. Okay, and let me actually erase this part. The next token that I am seeing is going to be 7. This is an operator, push it. The next token is an, that was an operand, you push it. The next token is an operator. What I am doing is, again, pop. So L will be 7. Another pop. R will be minus 26. You apply the multiplication over this, which I don't remember exactly what was the result, but I guess it should be, okay. $183, something like this. Multiply this to 26 multiplied by 7. By 2. Yeah, I guess that's going to be 182. Okay, it will be pushed to the stack, and then you continue. The next token is going to be an operator. Again, what you do is just one pop, another pop, so this part will be removed, another part pop, you add them, the result is going to be 177. I hope that I didn't actually make any mistake here. 177. And then another token that you read, it is an operator. Again, what you need to do here, sorry, it was minus 177. Another operator that you need to put, you need two pops. L is going to be minus 177. And then R is going to be another pop. This is going to be 1. You apply the operator, which is minus, so this is going to be R. O is going to be R minus L. Here the result is going to be 178. And this is going to be positive, right? And you push it back to the stack. You saw that even the stack became empty, but that's okay. I didn't actually see any error so far. So 178 will be pushed to the stack. You keep reading. 8 is an operand, push it to the stack. 5 an operand, sorry, 9 an operand, push it to the stack. The next token is an operator. You pop 9 and you pop 8, and the result is going to be, multiply them, the result is going to be 72. It will be pushed to the stack. The next token is an operator. You just pop this, 72 will be left. R is going to be 178. They are popped from the stack. You add them up and the result will go back in the stack. I'm sure that I probably have done some error in this calculation, but anyway, excuse me if I did. We will actually just double check at the end what was the result. But here the result of this one is going to be, adding these two is going to be 250. I'm sure it was not 200. I mean, the result was not 250, but anyway. Okay, something like this. I mean, we can double check here. And okay, before I leave, the thing is that I reach to the end of the string, right? Whenever you reach to the end of the string, at the end, the final thing that I need to apply, the result is going to be in the stack. You just need to pop the last value from the stack, and that is going to be the result, and just get it and print it in the output and whatever you want it to do with that. Okay, interestingly, I didn't make any error in this calculation. Anyway, okay, so this is the final result of that. You saw that the algorithm was very simple. It was just going over the input string once, and basically you can see that even the complexity of this algorithm is going to be O of n, because for each token you are just doing a constant amount of work. If I go back and check the algorithm that I wrote for you, you can see that then how many tokens you are going to have, for example, n number of tokens, and for each token what you are going to do, either you will apply this one or you will apply this one. Both of this is going to be constant amount of work, right? Because you are doing just 2 pops, 1 push here, or just one push here. So anyway, this is going to be constant amount of work. So at the end, for each token, you will do fixed constant amount of work. So in total, the time complexity here for us is going to be theta of n. Just it depends on how many tokens you have in your input string. And this is going to be a great algorithm. Just a couple of things to be careful about. What if there is an error in your input string? There are two possibilities that you might actually have seen some error. One of them is actually in this example. Let's just apply this or algorithm over this example and see that what would happen. You first see the token 2, it is an operand, you push it to the stack. The next token is an operand, push it to the stack. The next token is an operand, push it to the stack. The next token is an operator, you apply 2 pops, you get the result. The result is going to be 4, you push it back to the stack, right? And you reach to the end of the string. But if you look at the stack, there are 2 values in the stack. In fact, there is an operator which is missing here, right? This is 1 plus 3, and then you have a 2. What you are going to do with that 2 and the result of this one, which is going to be 4, okay? So an operator is missing and there is an error in your input. So one thing that you have to make sure is that when you are out of the loop, when you are at the end of the string, you have to double check that there should be only one item in the stack. If there is more than one item, it means that there is an error. Here is an example of yes, there is an error. You apply pop once and the stack should be empty when you apply the pop. For example, here at the end of the string, if I apply pop, 4 will be out. You check the status of the stack. If the stack is not empty, it means that there is an error. So you just actually just show that there is an error in your stack, in your input expression. So this is one way to actually detect some of the errors. The other type of error is this one. Look at this. Let's actually just see that how our algorithm is working on this. So the first token is 2, you push it to the stack. The second token is multiplication, push it to the stack. Sorry, the second token is an operator. What you are doing is you have to apply 2 pops, right? You would apply the first pop, L is going to be 2, and then you wanted to apply the second pop. And then you see that the stack is empty, right? So you cannot apply pop over a stack which is empty. And basically, it actually just tells you that this operator is missing an operand. There should be something before this one. And so you are missing an operand here. There is an error. And so you should be careful. Whenever you are applying the pop, before applying the pop, just be careful that you don't want your program to crash. Before applying each pop, just check the stack. The stack should have something to be popped, right? If there is nothing, it means there is an error. Just print an error message and make sure that your code doesn't crash. Okay, so here this example again has an error. You can just apply it and you will see that if you apply it, this is just a long example and we have already seen enough examples. Just apply it for yourself and you will see that at the end you would have more items, more than one value in the stack. So this is going to be a type of error. We have only 2 actually types of error. Either an operator is missing, that at the end you would have more than one item in the stack, or an operand is missing, that when you are popping 2 operands, you will see that there is a missing operand, the stack is empty and you can't apply pop. So there are only 2 types of error and you can catch both of them. So this is the end of this part. Just as a practice, we have seen the algorithm, right? Just try to write an algorithm for this, try to write a code
for the algorithm that we discussed here as an exercise for yourself. So